Okay. Oh, that's okay. Okay. Yeah, go ahead and sign in. Thank you for waiting for the technical difficulties. Then, all right, so we'll head on to the next slide. Welcome. This is GEM number 2. This is all about payloads. Oh, sorry. That's it's a spoiler for later. So this one's going to be all about payloads. Um, so this is just the GEM schedule again. We got flight dynamics coming up next Monday, and then we'll do structures the day after. Room assignments should be coming soon. And if it changes from what we have listed now, we'll let you know. All right. And then for payloads, we're going to be going through just like payloads as a whole. And specifically, we'll look at the mechanical systems, the electrical systems, the software systems. Then at the end, we're going to do an Altium demo. So first, what is a payload? We'll look at payload mechanical. So a payload is really just it's like any it's anything carried by a rocket that like does something special that a rocket on its own like isn't really meant to do. So that could be like some kind of sensor, like a suite of sensors, like a bunch of sensors that are all hooked up to one computer. I know last year for the NASA competition, we made like a plane that came out of the rockets. So there's a lot of leeway with the definition of a payload. So first for payload mechanical, this is all like the physical stuff on the payload. So a lot of payload mechanical work is CAD, especially at the beginning of the year when we're going through the design phase. Payload mechanical will do a lot of stuff with CAD, whether it be Fusion 360 or SolidWorks. And there's also stuff with like ANSYS if you're doing structural analysis to figure out like where you might need a little support here to manage the forces that everything's going through. Another big part of payload mechanical is your retention system. So a lot of payloads end up being designed to separate from a rocket. The example in this last slide is what our spaceport team did 2 years ago. It was a quadcopter that had these arms that kind of folded outwards after it deployed. And so one of the big challenges that they had is how do we stop it from coming out when the rocket's going like hundreds of feet per second? Because that would totally suck. So there's a bunch of different ways to do that. You could do like some kind of rack and pinion system. I know with the NASA competition last year, we had the plane come out of a door and we held the door closed with like a rack and pinion system. So in case you don't know, a rack and pinion is mainly made up of two parts. The rack is like a gear that's just like a flat line. So like all the gear teeth are just like on a stick. And then a pinion is like an actual gear that drives the whole thing. So we would have the rack as it got moved, it would like it would kind of lock the door in place and stop it from opening. And then when we were ready for the plane to come out, the pinion would turn and retract the racks, and then the door could open and the plane could come out. And you got to do a lot of stuff with mechanical and aero design principles. You know, whatever method you use to keep things in place, you got to make sure that it stays like within the bounds of the rocket, or if it goes outside of the rocket, you got to make sure that you're not going to mess with the aerodynamics. Like with that door for the payload for the plane last year, we had to really make sure that putting a door in a rocket was not going to like totally mess things up. And thankfully it didn't. So in the bottom right of this slide, we've got a little graphic of a little rack and pinion. And then kind of in the bottom left of the pictures, that's like the little sled that it was on. Those little X-shaped things are called 80-20. 80-20 is a really nice material. It's super, super cheap because it's really common, usually made out of aluminum. And it comes looking just like this, like in this X shape. So that's really convenient because the little flange over like the divots in the X means that you can like slide things into it and it'll hold it real nicely. Um, so that's something that's super, super useful for anything with payload design. As with any design, you always want to consider multiple designs or concepts. And even with the design that you do end up choosing, you want to always like be open-minded about changing things and making different iterations. Like nobody gets their concept perfect on the first try. Um, and a big part of this is looking at the mission requirements and restraints. There's less of this with Spaceport. Spaceport, they love you just like trying whatever you think is cool, going for any retention system. They're super big on like research and development. If you go to the NASA side of things, though, they give you a bunch of different requirements. They give you a lot more strict rules. And so you kind of have to get creative in a different way. Like, how can I make a good payload retention system and still like dodge a million requirements? And then you also get some constraints from the other people in your group or in the other people in your team. Like if you design a payload retention system for the spaceport rocket that's going to be like 10 inches in diameter, they're going to go up to you and say, hey, our rocket's only 6 inches in diameter, so change it. And then you have to work with that. And then next is balanced design optimizations with budget constraints. Budget is a big thing with engineering. You can make the greatest design in the world, but if it costs $1 million to make, we're not going to make it. So you have to make sure that whatever you're making is cheap to make and easy enough to make that like it's possible and practical to make, but it also has to be something functional. You know, a cardboard box doesn't make a good payload retention mechanism. And then, of course, design with the ability to make changes. That goes back to iterating on your design. There's always something that's going to come up. Something's going to work not how you expected it to. Some things might just not work at all. So you need to be able to change things as the year goes on. And, you know, sometimes that's just a part doesn't work how you want it to. Sometimes that's the competition kind of like changes up in the middle of the year. Like they may add some random like specification near the end that maybe you just like didn't realize was there at first. And so you just need to be ready to make changes as they happen. And then design finalization. Anytime you have your final design, you want to look over at like the big picture and see like, does this really make sense? Or have I kind of like over designed things? Have I made things more complicated than they need to be? Are they more expensive than they need to be? Then you want to look at considering the materials used and the selection criteria. So whenever we're selecting materials or I'll pretty much like any big change or big decision on the rocket, we use what's called a decision matrix. And that's just kind of like you define a few different like properties of your payload. So that could be something like cost, time to manufacture, weight. And for your different payload designs, you kind of compare those metrics for each of them. And then each one's weighted a little differently. So you might say, well, we really care about the weight. So if the weight of one thing is really good, then we might prioritize that, even if it's a bit more expensive. And then you go through the decision matrix, and that helps you figure out which design is like objectively the best. And that's big for considering materials for aerospace. The big materials are like aluminum is a huge one because aluminum is very light for how strong it is. Carbon fiber is a big one. It's very stiff for also being even lighter than aluminum. Like the spaceport airframe is made out of carbon fiber, for example, because it's very, very lightweight, but it's still pretty stiff. It'll keep its shape pretty well. And then you got optimization to finalize design prior to manufacturing. again, that's something with like taking a look at the big picture and seeing like, is it actually possible to make this thing? Like if you need to make like a cube with a sphere hole inside of it, then you kind of have to think like, how the heck am I going to drill a sphere inside of a cube? And it's not really going to work. So you have to kind of look back and make sure that whatever you're designing is actually manufacturable. And then the last one is providing clear evidence that design has been proven. That is where you go to some tests and where you look at, okay, we need the payload to do this. We need the payload to be able to handle this. So let's actually put it to the test. So there's a bunch of different ways that you can do that. Sometimes you can kind of divide things out into their own little sections and work on those individually. Like if you're looking at something like a transmitter, then you don't need to get your whole payload ready for that. You can just hook up your transmitter and you can hook up a receiver somewhere else and make sure that everything works fine. But some things you really have to make sure that they all work together. So like for this drone, for example, you got to make sure that it actually flies. And so for that, that's something where you'd put the whole payload together and then you could do a flight test, maybe just off the ground. And then you might think something like, well, it can fly when we take it off from the ground, but is it going to be able to fly when it comes out of a rocket? And so that's something where you may want to do a full scale rocket flight test or maybe a subscale rocket flight test to save a little bit of money. That way, when you go to competition, you don't find out on competition day that what you've been working on doesn't actually work. So yeah, that's more with assembly and testing. You got to go through the whole manufacturing process. That's where you really get your hands dirty in the lab, make everything that you need to make, and then put it all together. And then that's when you start off with your tests. Testing individual components for failure and strength. That's what I was talking about earlier with kind of breaking things up. So the transmitter was just one example, but you can also do things with like materials. So you could like, if there's a part that you're worried might break from some forces, you can do some materials testing. So that might be something like using an Instron in the mechanics and materials lab, something like that. And then, of course, testing the full assembly. So on the left there, you've got, that was their like ground test. They put down a little tarp to have a nice clear surface for the drone to take off from. Because in theory, it's going to be taken off in the air after coming out of a rocket. So they don't want the grass to interfere with the takeoff procedure because it's not going to interfere anyway. And then on the right, I forget what that is, but I think that was just making sure that the whole thing would like right itself after coming out of the rocket. And then, yeah, it looks like more tests of that in MAC. And dang, that picture is like so warped. Okay, so next we'll go into payload electronics. I'll hand it off to Michael.
Hello. All right, we're gonna get started on the electronics. I'm gonna try to go through this quickly so we have time for the demo. We'll see how it goes. Okay, so the basic components are going to be a processor of some sort. This could be like a Raspberry Pi, an Arduino, something lower level like an STM32 chip, some sort of ML chip. It really depends on the application. Usually we'll have sensors as sort of peripherals because you have to be able to get data in order to control your payload, unless you don't want to control your payload, in which case you don't need sensors. Yeah, usually you have some actuators like servo motors, DC motors. Sometimes you'll have stepper motors. It really just depends on the application. Yeah, and then your power systems pretty much almost always are going to be battery for you're mainly powering everything, and then voltage regulators to power your subcomponents. So those will take your battery voltage down from like, let's say 9 volts to like 3.3 or 5 volts or whatever your other systems are running on. What is a PCB? As the slide says, it's a platform for creating circuits without needing external wires for each individual connection. On a PCB, it's basically copper traces, which act as your wires in multiple layers with like insulation on top, and that allows the electricity to flow as copper is a conductor. The reasons for this are spaghetti how. Really, you don't want to like prototype on proto boards with lots of wires if you can. It gets very confusing and debugging becomes a nightmare. And you really, really, really don't want to do it. It does require, as that says, more time earlier in the design, but it's like really 100% worth it. Because then if something's broken, you just probe around with an oscilloscope, maybe you have some status LEDs, you can like look at the board and see what's working and what's not working. And then you go back and you iterate upon your design. So the process of creating a PCB is first you have your schematic, and a part not noted here is oftentimes in a standard library, like when we go to do the demo later, the university has a standard parts library. Oftentimes your components that you need for your schematic won't be in that library. So you need to create the symbols for them yourself and create the footprints as they would appear on the PCB. The footprint is like how much space it takes up on the PCB basically, and where the pins are. So yeah, schematic design, PCB layout. So after you have your schematic, you bring it all into a board, then you order it, which Chinese manufacturers like JLC PCB or PCB will make this really easy. You just export your files that define the geometry of your board. You put them into their website, and bang, you have a board. And then the last step is to assemble, which usually means soldering everything on. Depending on the complexity of the board, you can pay the company to solder everything on for you. Or as I believe the next slide says, oh, it doesn't say this. You can pay the company to create like a stencil for you, and then you can just put solder in the stencil with your components, and that makes it much easier. Yeah, schematic design, they define how everything is connected. You can use a variety of different components for this thing. Yeah, the layout is the size and shape of the board, as well as how the traces are routed to each component. Generally speaking, you want to keep your traces as short as possible and minimize traces on the ground plane. This is to do with parasitic capacitance, which basically, when you're sending a signal, if you have too much capacitance, it takes energy away from that signal. And what could happen if there's too much is the signal could disappear or go unstable, and you won't have the intended effect of the board. Yep, this is pretty much what I was saying earlier, where you can buy stencils. You want to use solder paste when possible. It makes it much easier. And for soldering, you don't want your temperature too high, or else you will burn the board and components, which usually, at least for the board, is not a problem. But sometimes for components, they have this thing called like a solder reflow curve or what have you, where it will actually damage the internals of the components if your temperature is too hot. And one more thing I would like to say about electronics is that data sheets are really your best friend. Sometimes I won't even pick components if the data sheet is not detailed enough or like it doesn't meet your requirements, obviously. All right. Next is on to software. So software is done in a variety of languages, really depending on your platform. If you're using more of a Raspberry Pi Arduino type of deal, well, for an Arduino, it would be in, I think they have their version is like C# or whatever. But for a Raspberry Pi, you can pretty much choose whatever. So Python, C++. Java, if you're working lower level, then it's going to be C primarily. Yeah, as it says, it's not dependent on the rocket. It's dependent more on the payload. And really, when you're designing software, you want to plan everything ahead and then begin writing the code. I'm not going to lie to you, I don't always follow this practice. Usually I'll start writing code and then the flowcharts come later, which is not always great, but you really should if you're trying to get it right the first time. Flowchart first and then code second, though it probably still won't work the first time. Oh, here's, oh, I thought this was a video. I guess it's just an image. Is it a video? It is a video. This is them testing the software for a drone they made 2 years ago and seeing that it will right itself from instability. Okay. And now it is time for the Altium demo. Oh, yeah. Okay.
Yeah, go ahead and do
I'm gonna try to do this quickly. Is this not gonna work?
That's pretty much the last part. So you got about 30 minutes.
Okay, I might not be able to do this without an HDMI cable. Oh, I can't because my license on my laptop takes up my full licensing.
Well, wait, I think there's an HDMI cable.
Uh, oh, there is. Okay,
Yeah, go ahead, plug it in your laptop.
let me close this. Hold this. Okay. GM awesome demo. And then I'm creating an empty PCB project, so there's nothing in it. And then you just hit create. All right, and once you've created, you'll see over here this project folder. This thing will contain all of your subfolders in your project. Everyone go with that? Cool. Once you're there, you can right click on that and you can go add new to project schematic. And just like that, you have an empty schematic, which you're going to want to rename. You don't need to rename it to the name of the project, but I will for fun. But you right click on it, you hit rename, and that renames it. Because there's only one schematic in this project, it's fine if I give it the name of the project itself. Once you're here, if you go to panels on the bottom right, you should be able to get to components. There we go. And it should come up something like this. Presuming you're logged into your UFL stuff. We're just going to use default components from the UF library. Doing more than that would take too much time for this demo. Once you're here, what we're going to do is we're going to create a very simple circuit, which will just be a microcontroller, which through its one of its output pins will be able to turn on an LED. Is the basic idea. And so the first component we're going to go look at is if you type into the components bar at Mega 328.
Oh, Mike. There's a question.
Oh, yes. Yeah. Okay, so if you go to the bottom right, there should be a thing which says panels. And then click components. And it should have like it should come up with some components, and then there should be a search bar at the top of the components menu. Yeah. And so at Mega 328, we're just going to select the first one. Each of these have different footprints and probably different pinouts. but we're just going to select the first one. You can right click on it and press place. Is the easiest way to do that. And then you can just left click to put it in your schematic. And then when you don't want to place anymore, you can press escape. And that will take you out of that. We're going to need a few more components. We're trying to drive an LED here. So we need the LED, which I'm going to pick. If you just type in LED, or actually, this is the one I found earlier. We're going to do TLMB11 0. It's this LED. This thing has a forward voltage of 3.9 volts, and this circuit would actually work in theory if you were to make it. You're going to see this component. You're going to come in. You're going to place it again. Press spacebar to rotate components. And then it's just left click to place, escape to stop placing. Everyone good? Yeah.
You don't see the components when you see, like when we type in add mega, it's not.
It doesn't come up?
Press the button that says manufacturer part search, it brings up all the ones that are thing. And so that's.
Oh, it should, yeah, it should also be in your like regular components. It could be because are you signed into like the UF, like your UF stuff or?
Oh, my searching up, this is like an eight there.
Hmm?
Like I.
Let me see what's going on. Oh, yeah, so you want to come to here, so I can like see this cloud icon like that. You want to activate something slow. Oh man, this is gonna might be an issue. Okay. So the reason this is not working is because at the I didn't realize this would be an issue, but at the top right, you'll see like some cloud icons that say not connected. If this is your first time using Altium, and you're gonna want to click on those and then click activate workspace, and then set that up. And then ideally that should give you access to the component standard library for UF.
It brings you to a website.
Yeah, it brings you to Altium 365. That's what I'm saying. You have to go through this.
Okay, is the workspace like UF? What?
It just creates like a generic workspace, but then it's like connected to UF and you should get all these components. Should. I believe that's how it is. I'm sorry. I've had this program for a minute. I didn't realize this would be an issue. See if this works, and maybe we can avoid this.
That's how I pulled mine.
I mean, let me see if we can avoid this. If I can just, yeah, okay, let's just do it this way. Don't you not do what I said and just go to manufacturer part search and then right click on this and save to my workspace, and it should be fine. Okay, I'm sorry. I'm gonna continue with the demo since we're sort of running low on time. I'm sorry if you guys can't like pull all this stuff up. But
Yeah, we'll post a recording of this
yeah.
afterwards.
Okay, so then we need a resistor for the LED so it knows how much current it needs. I'm gonna go with a 100 ohm resistor. There should be some options in here. Let me go to resistors 100, and this should give some 100 ohm options. Where's an 100 ohm option? Okay, here's an 100 ohm option. Like you could probably go like 100 ohm resistor, and something similar will come up. So we have our resistor, and then we're gonna go ahead here and assume that the power supply is coming from some voltage regulator, and then it's standard practice to, I say standard practice, it depends on what microcontroller you're using, but generally manufacturer recommendations will want you to have one 0.1 microfarad capacitor in between each power and ground connection, or that's the same as 100 nanofarads. I'm gonna go ahead and pick this one. And so we have a VCC, an AVCC, and an AREF. We're going to ignore the AREF. That has to do with an analog to digital converter. It's not necessarily the best practice to leave it floating, but in this case, it's fine since you can select the reference to be AVCC. And it likely wouldn't cause any issues, though that's not necessarily the best practice. Okay, we have that. So we have two of those. And then the last thing we're going to want is we need some header pins. That way we can give power onto the board. And for that, we're going to use S2B, XH, not in capacitors, in all components. S2B, XH. Here we go. And these are just like some generic 2-pin header. In reality, you would need more than this because different ways to program this microcontroller would call for different pins to be used. But just for this demonstration, we'll assume this is good enough. To zoom in and out, it's control and then scroll on your mouse. I have no idea how to do it on trackpad. Okay, so once you're here, you pretty much have everything you're gonna need. And so all your components need to be grounded. So to do that, you can come up here, place ground power port, place them, spacebar to rotate, place them here, place it here. You want to make sure you see this like X light up red because that's how you know the program knows that it's connected to the pin it's supposed to be connected to. Then for your capacitors, they're supposed to go between ground and power. So ground here. And now we want to specify what our power is. You could do VCC, but I prefer not to do this thing. So what you can do is you can pull your ground power pin. You can press tab, or yes, tab. And then that brings you to this menu where you can edit its properties. This works for any component, by the way. You can edit properties this way. So we want 5 volts. And then we want to change the style to a bar just because that's typically what is done. And now I've edited the property and I can go ahead and place that on my capacitors. And then I can also place it at the appropriate power pins. And additionally, these pins over here, it's going to be one to input 5 volts and one if you want to get your 5 volts back out. So we'll have those two here. What this does is it like connects them in the software's internal logic. So you'll see when we go to the PCB, there'll be like little lines going between the pins of the components to show you the stuff. You hit tab, and then it takes you to this properties menu, and you change the name. And then you also go to style, and you change it to bar. Okay, and you'll see that there's these like red squiggly lines. That's an error because this says C question mark. It's because you don't actually have a designator for these. A designator is just something which tells the internal program like what's going on, what components are what. We'll get to that in a second. It's sort of like Microsoft Word in that way. Okay, so the last thing is going to be, let's say you don't want to use net labels, because sometimes there's reason not to, because like it doesn't make sense or it just makes things more complicated. You can come up to here, you can go place wire. So like if I was wiring this guy to an output pin of my microcontroller, you can go with wires, and that'll connect it like that. And then these two things are connected. And when we go to the PCB, you'll see they're connected. The other thing you can do is you can place wire, and it's always escape to get out of whatever placing mode you're in. You can do things like right click on it and edit the properties of this thing if you really want to, like change the size and the color and all this sort of thing. But you don't really want to, you want to keep your stuff pretty uniform. And the default settings are usually pretty good. But what you can do is you can right click on the schematic. You can go to, where is it? Place, and then you can place net labels. And this is basically the same thing as the power ports, but like different notation. And you can set different, in the software, you can set different design rules for these things. And it makes a little bit of difference. I don't know what the default is. Right now I have mine called LED out. If you press tab, once again, you can edit this stuff. We change it to LED output even, and then can escape. And then we're good to place these here like that. And then these are connected. You don't even really need these wires. As long as they're connected to the pin, it's fine. But yeah, and so this is a very basic schematic. Once you're done with that, you're going to want to save. You can also Control S to save when you're on the selected thing if you want to. But now that everything is saved, we have our schematic. So the next thing you're going to do is right click on the project again, add new to project, PCB. Give it a second to load. It's loading. All right, there we go. And so now we have our PCB, but you'll notice there is nothing here. And that is because, well, for one, we need to rename it. I'm gonna once again rename it GM, awesome demo. So we're gonna rename it, and now it's saved renamed. Then you're gonna go ahead and go to design, import changes from GM awesome demo project PCB. So what this does is it takes your schematics and imports them into the PCB. And because I was using like the stuff that was already in my library, the footprints are done for you, and the pins are done for you, so you don't have to worry about that. All you have to do is import. Once you import, you want to validate your changes always, because sometimes it'll tell you it can't make changes or there's conflicts, and you can either manually resolve those or you can suffer the consequences. It's sort of like a bad merge on a GitHub, which could break all your things if you're not careful. But you get all good check marks. You can hit execute changes. And it takes a second to execute. And then I can close this. And if I come over here, all my components are now in my PCB. And if I hit 3 on my keyboard, like the number 3, it takes you to a 3D view. And you can see your components and the currently defined size of the board. If you control scroll wheel, you can zoom in and out. And if you shift, you can rotate your camera so you can see everything at all the angles in all their glory. I'm going to switch back to 2. And so this board is way, way, way too big for these components. So what we can do is you can either come up to here to place, or I prefer just right clicking, place. You can either place lines and define like a custom shape, or you can place rectangles. You can also, there's a way you can do like squiggly lines and do like circles and stuff to define your board shape. I don't know how many manufacturers are able to do that, but you can. But the easiest thing to do is you define, so you click place rectangle. Oh, I'm in the wrong layer. I lied. You want to be on mechanical 1 because that will define your board shape. And then you come to place rectangle, and you can create a rectangle that's like roughly the size you need it to be. that's probably good. You can always adjust this thing later by selecting the different parts of the rectangle and this sort of thing. But once you have defined the shape you want, you can go ahead and go to design, board shape, and then define board shape from selected objects. And it looks like, bam, we have a board that is roughly the size we need it to be. And so from here, what you can do is you can drag your components onto the board and it'll automatically handle like the footprints and stuff. So you probably want your microcontroller maybe to be like in the middle. Oh, you know what I forgot to do? I forgot to talk to you about designators. I'm surprised it's not more confused. I lied. Go back to the schematic. If you come to tools, annotation, annotate schematic, you can sort of leave these things default. This determines how it numbers your components, like up and across and down, whatever you want. We're gonna go with this. You hit update changes list, fix changes made, accept changes, validate changes, execute changes, same as with the PCB. If it has issues, that could be a problem. Then you want to save this. Oh, we'll actually get to use the update feature. Let me save this one too. Now what we want to do is come to design, update schematics, and it should. I don't know why it's complaining, what it doesn't like. I don't know, but executing those changes is fine. Is not fine. Man, I don't know what happened. Okay. Oh, they didn't annotate here. That's weird. Um, update dot no. I wanna tools, annotate thematics, update changes list, accept changes, close. Huh? Okay, I don't know why this is not working. That's strange. Just one more time. Update changes list. Accept changes and create ECO. Validate changes. Execute changes. Close. Okay, there we go. I don't know why that was doing that, but now we have changes. And then let me save this. And then let me make sure I don't mess this up. Design. Import changes from schematic, and these things should show up numbered. Okay. There we go. Okay, they all executed, no problems. Okay, now we're good. I don't know why I was doing that. I've never had that happen before, but you can drag your components onto your board. Like these are your decoupling capacitors is what they're officially called. You can rotate these things with, you should be able to rotate them in the properties. No, it's in the properties for this menu. I believe. If it'll let me select the components. Yeah. But regardless, you can drag your components in. This is your LED, your resistor. You want your capacitors near your power. Okay, and so once you have that, you can save it. We're saved. And now what you want to do is you want to route. You can do this. We'll start with the option you should do, which is interactive routing. And then I'll go to the option, which is black magic and is not necessarily a great idea. For you go to route interactive routing. Once you're there, if you zoom in, actually, you can see the different nets of your parts. If you click in the middle of a pin, it brings up your ability to route. and it will do its best to route to that location for you. There's some degree of auto routing here. And you can mess with it, but like I'm going from 5 volts to 5 volts since that's a net. I want them to be connected. And then I can keep doing that between all my nets, or like if I want LED output to LED output, that's going to be to this net, and you can sort of do your best for that. The other option, which for very simple boards is fine, but once your boards get complicated is not fine, is you go to routes, and you go to auto route, and then you hit auto route all. You can also auto route individual nets and connections if you want. This is sometimes it glitches, so you don't really want to do this for very complicated boards. But like I said, simple boards, it's not really a problem. You can select the type of board you want, and presumably you could add things to this if you wanted to. And then you just hit route all, and then it does its best to route everything. And just like that, you have a routed board finished with, oh, it failed. Okay, well, that's why you don't use auto route because it fails sometimes. But that's the idea. And then if you come to your 3D view, once again with the 3 key, you can see all your components routed in all their glory and whatnot. And this is a very basic board. And if you included some pins for programming this guy, in theory, this thing could work. Yeah, thank you. That is my demonstration.
Okay, so just like the open rocket demo, if y'all could DM that to me, I'd appreciate that. Your Altium files. Can you show them how to save the file?
Yeah,
Or like how to,
oh, to export?
yeah, export it.
Yeah, you can come to make sure this is selected. File.
The FP file.
What do you think, Michael? What would be best for them to send over?
I mean, that's probably fine.
Okay,
I mean, I don't.
That's fine.
I don't think a lot of people.
Yeah, I don't think it was
Yeah,
working
it's
for a
all
lot of
good.
people.
Just do your best with it. That's all good.
Yeah.
Yeah, this will be recorded, so we're gonna post this.
Yeah, so you can come here and you can export it in a specific format, but what I would actually recommend doing is if you save it locally, you can just find where it's saved locally and send that is probably the easiest thing to do. Like zip up the project, and then
There's a command with them, but.
I don't know. I don't do this very often. Usually I'm working on my own project, so I'm not
Yeah.
100% sure. The answer is probably, but you can also just go to where it's saved.
Probably sent that to you, Zip.
Yeah, you can send it on zip, but the project file will contain all this other stuff. So you want to make sure that like all your stuff gets sent, which is why you want to zip it. No, the project file contains the sub files. So you want to zip it up so that when you send it, it has the sub files, and then someone can just unzip and import pretty easily.
So yeah, DM that to me on Slack, Reed McAdam. Just whenever you get the chance, I'd appreciate it. And then we can head back to the PowerPoint.
Yeah, and then to close the project, I should have said this. You literally.
Okay, we got one more thing.
Yeah, I forgot to close the project. Is literally you right click on it and then hit close project, and then we're done. Okay. Let me unplug from HDMI.
Okay. Okay, so the last part, oh, that's your mouse, sorry. For the last part, we finally have our certs application. I'm also gonna post this on Slack, so you don't have to fill it out right this second. I'll have it posted tonight. Again, this is for a level 1 certification through the National Association of Rocketry. You have to fill out the application to be eligible for selection. And what we at Swamp Launch do for this is we're going to kind of guide you through building the L1 rocket and like getting your certification. All in all, the cost is $180. The application is free, but if you get selected, the cost of materials and getting a NAR membership, all in all, is about $180. So that's something to keep in mind if you want to do an L1. And then we're gonna schedule our manufacturing sometime on the week of September 30th. And then the cert's launch date will be on either October 19th or October 20th. You have to be able to make either of these dates. We're not sure which one it is yet because usually they only give one launch date, but for some reason they're giving two. We're trying to figure out why, but for now, while you're applying, make sure that you're available for both. And chosen members will be notified on the 26th. Yes.
So when you're taking the chosen members through, are they building their own rocket or is it everybody's collectively working on one?
Everyone's building their own rocket.
Okay.
Mhm. And then-
Is something Swamp Launch does to get everybody like up to speed or just like go through the certification process and
Yeah, exactly. This is like your own personal thing. You don't have to get a certification to be on the team. You can go to any meeting you want without a certification, but this is just like if you want to build your own rocket, get a cool certification, something to put on a
Yeah,
resume.
this is true. I am uncertified.
Yeah, he's not certified. Yes.
You get chosen, if something comes up, would you be able to respond to in the spring?
Yeah, we might be able to. That's what happened with me. Like, I signed up for a fall one at first, and then something came up for me, and I ended up getting moved to the spring. But it's not completely guaranteed.
what time do the launches usually happen? Is it a morning or night thing?
It's a morning thing. They have to launch during the daytime. And it's kind of an all-day affair because the closest launch site, which is the one that we're going to, is in Tampa Bay. So it's 2.5 hours drive down, and then we have to launch, and that takes we have to set up and then launch. That takes a few hours, and then 2.5 hours back up. So you really have to plan. Exactly. Well, 19th and 20th are Saturday and Sunday. So I don't think you have an exam, unless they give you one on the weekend, which that kind of sucks. Yeah. But yeah, 19th and 20th are Saturday and Sunday. And yeah, this is like an all-day thing. Launches take a lot of time. Okay. And then looking into the future, on Monday at 6 p.m. And actually, I believe this room got changed, but I'm gonna post on Slack what the correct room is. It got changed just a little bit ago, I think. We're gonna do avionics and recovery, and we also are still figuring out what to download for the demo, so that will also be announced. It may end up being MATLAB, which that you don't have to download something for, but I think there's a good chance it's going to get switched to something else. But that'll be on Monday, and I'll announce all the details before we get to GEM time. Then, as usual, we got the Slack and the Instagram. And yeah, thank you all for coming.
Just go through your apps.
Yeah, I don't think they're going to.